Lightning testing. Thank you for joining us. This webinar is being given by MET Laboratories. MET is a leader in the testing of electrical and electronic equipment for environmental hardiness, product safety, and electromagnetic compatibility. MET operates world-class labs in Baltimore, Maryland, Santa Clara, and Union City, California, Austin, Texas, and also runs operations in China, Taiwan, Korea, and Italy. This webinar will run 30 to 45 minutes with an additional 15 minutes for questions and answers. Due to the number of registrants, all attendees will have their phones muted. If you have a question, please type it in the questions area of your control panel. We will attempt to answer all questions at the end. If you're having technical difficulties, you can contact us the same way, or if you can't, you can call us at 410-935-6053. Just a quick note on other upcoming events. In September, MET is hosting a free military and RTCA testing seminar in Baltimore, Maryland, where we will also discuss lightning testing. You can register for this event at www.metlabs.com. Today's webinar is being presented by Asad Bajwa. Asad is the Director of EMC Testing for MET. At this point, I will hand over the presentation to Asad.
Thanks, Bernabe. Hello, everyone. My name is Asad Bajwa. Today, we are going to talk about lightning-induced transient susceptibility with the special focus from Section 22 of DO 160. So let's go through that. Here is a brief outline of my presentation. We'll talk about what the lightning is, what the needs for the lightning testing are, and how this plays a role. We'll talk a little bit about the background of DO 160, what are the bodies who are responsible for taking care of the Section 22 and similar lightning testing. So we're going to briefly talk about that, and then we're going to dive into the lightning testing itself. We're going to pick some of the waveforms. We're going to talk about some test requirements and test methods. Well, the DO 160, the latest rev is Rev G. Over the years, we have seen from Rev D all the way E, F, and G. As the name states, it talks about the environmental conditions and test procedures for airborne equipment, the commercial aircrafts. The Special Committee 135 of RTCA, which is Radio Technical and Communication for Radio Technical Commission for Aeronautics. Special Committee 135 is responsible for this particular standard. It talks about the environmental conditions. It talks about the test procedures, and for the airborne electrical and electronic equipment. So if you look at the DO 160, broadly speaking, we can divide DO 160 into two sections. The first 14 sections cover the environmental conditions which will apply to an electronic product which is going to go into an avionics environment. And from section 15 onward, the requirements are related to the power input to the electronic equipment. They talk about some of the EMC, EMI, including the lightning, which is section 22. DO 160 partly also cover the FAA requirements. Another way to put it is that FAA requirements are based on the DO 160. However, they may have some additional requirements on case-by-case basis. Some of the references, as I mentioned earlier, the latest rev of DO 160 is the Rev G, which came out in 2010, and before that, the Rev F came out in 2007. Another reference I have listed there is Mil Standard 461F. The reason being that there has already been discussions about when the Rev G comes out of 461, we are going to borrow section 22 from DO 160 and incorporate that into Rev G. So when that happens, and the discussion been out there since 2012. So whenever that happens, from that point moving forward, for MIL standard 461, the lighting will also become a requirement. Okay, let's briefly talk about what the avionics is. Well, as the name states, avionics is the electronic equipment on an aircraft, commercial aircraft. While we're talking about the commercial aircraft, well, the first thing which comes to mind, if we look at historical basis, that avionics sound like the navigation and communication equipment. However, with the advancement in the science, with the advancement of the computer-like devices like tablet computers, smartphones, the advancement in the communication in terms of the internet, the Wi-Fi, the cellular communication. So all the above can and do go into a commercial aircraft environment. So the definition of avionics have expanded. So we will have to look at a larger picture that now there's a lot more equipment which could be very, very mission critical for a given application is going into a commercial aircraft. And then thus the effect of the lighting is not only going to affect the navigation equipment, it's also going to affect the communication equipment, and it could apply to all the other equipment or categories I mentioned earlier. In some cases, we see that there are medical equipment, for example, the breathing devices like a nebulizer or others, they also find their way into the commercial aircraft to treat the patient should there be any emergency. So when we talk about the lighting effects, we'll have to collectively look at all the electronic products which could be in a commercial aircraft environment. I briefly mentioned about DO-160. Just want to state one more time, the RTCA is the Radio Technical Commission for Aeronautics. Every 4 to 5 years, they come out with a new revision. And today, what we're going to focus is on the Section 22. Another bit of information which may come handy is the, I would like to mention about SAE. SAE, as the name states, Society of Automotive and Aeronautical Engineers. The subcommittee AE2 is the body which is predominantly responsible for taking care of Section 22 of the DO-160. If we try to draw parallel with the European requirement with the, as far as the avionics equipment is concerned, the European body, Eurocade, is responsible for the avionics equipment, and the publication ED84 is practically the same as the requirement from DO-160 Section 22. Okay. I mentioned about MIL Standard 461. I would like to mention again that everybody in the industry has been waiting for Rev G to come out. 2012, the talk was that this standard, this new revision will come out, and the lighting will become a requirement for military aircraft as well as it is for the commercial aircraft today. However, for budgeting reasons and some other reasons to harmonize the requirement among the agencies, whether it's Air Force, Army, Navy, and others, they've been delayed. There have been significant delays. Now the talk is out that perhaps sometime this year, later this year, 2014, the Rev G will come out, and the Section 22 will find its way in one way, shape, or form into Rev G, and thereby those lighting requirements, in addition to some other requirements, will become part of the 461 family. Okay, jumping right into DO-160 Section 22 lighting, as the name states, we're gonna talk about lighting with a special focus on the indirect lighting. The main difference between the lighting, when we talk about indirect and direct lighting, we are looking at two different phenomena. The direct lighting would be when it hits a metallic structure or a device or an electronic equipment directly. When a lighting is hitting directly, the concerns are different. The concerns are to ensure the overall integrity and safety of the equipment and personnel around it. When we talk about the indirect lighting, the intent is to see by performing the testing, when the lightning hits, it's going to cause or induce currents, and when those currents develop more electromagnetic field inside the structure of a device, or we're talking about the avionics equipment. So let's talk about the structure of the a commercial aircraft, then how those induced electromagnetic fields will find their way, and how would they couple to various harnesses, various electronic subassemblies or equipment within the commercial aircraft, and what would be the implications. So that is the whole intent of the Section 22 testing. Now the question comes, who will need the testing? We've been talking about the avionics industry. So obviously the aircraft manufacturer or the contractors or subcontractors who are building parts or the components or assemblies or sub-assemblies for the commercial aircraft manufacturer would be the ones who will need to go through the testing like the 160, where they would need to, where their assembly or sub-assembly will be installed, will need to do the indirect lighting testing in some cases. If the product has a external antenna which is protruding out of the structure of the aircraft, the direct lighting may also be applicable. On this slide, I have listed many of the worldwide aircraft manufacturers like Embraer, Bombardier, Airbus, so on and so forth. When we are talking about the lightning, it perhaps will be a good idea to have a brief conversation about what the composite materials are and how they play a role. If you look at a conventional commercial aircraft, which are being built for decades and decades, historically all the frame is made of metal, or called metal frame, and when there is a good metal-to-metal connection, which obviously is the assumption when we talk about a commercial aircraft, then the overall structure, metallic structure of the commercial aircraft provide a very good shielding, or what we call Faraday cage, thereby when an external electromagnetic field or a lightning which will induce electromagnetic field hits the commercial aircraft metallic structure, then the threat, by the very definition the metallic structure is providing shield, is reduced by many folds. However, concern could still be that what if there are some ruptures, or what if there are not a good metal-to-metal connection, or there are some non-metallic structure on the plane, like the case always would be, then obviously study would have to be done, testing would have to be done to look at that. But point being, considering a complete metallic structure of a commercial aircraft versus what we are seeing today, where with the advancement in science, where the development of the composite materials, they are getting cheaper, they are easier to produce, building of the parts, commercial aircraft parts out of composite material is a lot more convenient, simpler process as far as the manufacturing is concerned, compared to building the pieces and parts from a metallic sheets like aluminum. So thereby, composite materials are finding a lot more their way into the industry, where we see today that many of the surfaces or structures of a commercial aircraft would have composite materials, which in a way is a good thing. However, the downside of having the composite materials in a commercial aircraft is that now we are, by very definition, compromising the structure which was providing the shielding or which was providing a perfect Faraday cage. And therefore, when a lightning strikes to a commercial aircraft where there's a lot more reliance on the composite material, the concern would be that lightning will have more prominent effect to the assemblies or sub-assemblies, electronic equipment, avionics equipment inside the aircraft. So it will become a lot more of a threat. It will become a lot more of an issue to ensure all the avionics equipment within our aircraft, which has composite surfaces, or which is relying on the composite material, that those avionics equipment are designed to be hardened enough to deal with the indirect lightning threats. That being said, let's look at an example of another commercial aircraft where we can see where the tail parts or certain parts of the wings are made of composite material, and by very definition, Faraday cage is compromised, and thereby the threat of the lightning becomes more prominent. Okay, continuing on, this slide is an overview of the Section 22 requirement. I'm going to just briefly mention a few important items, the highlights. There are 7 test waveforms which go from all the way from 1 to 6. There are 5 test levels 5 being the highest one. There are 2 main test types or categories. One is called injection, which is done on the connectors, and the cable bundle, which is done on all the cable bundles by the induction method. We use the clamps to induce those signals onto those cable bundles, cable assemblies. Then there are three different test methods. Call them direct cable induction or ground injection. And there are three different applications: single stroke, multiple stroke, and multiple burst. And I have one specific slide where we will talk a lot more about what is the difference between single stroke, multi-stroke, and multiple burst. Then there is a talk about the category designation. So just a few words about the category designation. When a lab gets a request to perform testing, or a contract is being signed, or perhaps when a test plan is being written, if you look at the Section 22 talks about the category designation, which is with the new rev of the standard, it has 6 characters or a combination of numbers and letters. So if you take this first example on this PowerPoint, I have B3, G4, L3. So let's see what it means. B3 means the waveform set B from Section 22, and 3 signifies the level 3, which is basically relevant to the direct testing, the direct testing method. G is the waveform set G from the standard and level 4. And L is the waveform set L and the level 3. So the number after each letter signifies the severity of the level for those waveforms which are coming from these various waveform sets. In this case, D will be a waveform set, G will be a waveform set, and L will be a waveform set. And they come from straight from the various section of the Section 22 with the description what each waveform is. Okay, if I could, yes. So this slide is basically a summary of all those 7 waveforms I mentioned earlier. Starting from waveform 1 to 6, what we can see is majority of these waveforms are double exponent. I'm not going to read everything on the slide. I'm just basically going to state that the waveform 1 is the current waveform. Then going from waveform 2 to 4, they are voltage waveform, and going from waveform 5A to 6, those are current waveforms. So what it means is these waveform parameters are defined either as a current waveform or a voltage waveform based on the statistical data which was captured historically to determine what would be the threats to a commercial aircraft from the indirect lighting. This is how the waveform 1, the current waveform, will look like. Waveform 2, 3, waveform 4, and waveform 5A and B, which are the current waveforms. Waveform 6. Okay. Now let's talk a little bit about the various test levels, what they mean. If you go from test level 1 to 5, level 5 are obviously the highest level, the most severe level. So those levels will be used to test an avionics equipment for 2 reasons. One, it's an extremely mission critical equipment. There is no room for any failure, or there is no room to take any chances, or this product will be, or this device will be, or this avionics equipment will be used in a very adverse electromagnetic environment where the threat of lightning is very, very high. Level 1 will be used in those equipments which are very, very protected. There is a very good protection, like it's a very good design, metallic Faraday cage, where the lightning, if it does happen, it's going to be protected from the external shield, and the chances the lightning will find its way is next to none. So therefore, it's considered sufficient for those protected environments. The testing is done for the avionics equipment just to level 1. Now let's talk about the test types. Pin injection, cable bundle, as I mentioned on my earlier slide. So pin injection test is basically comprised of the waveform 3, 4, 5A. This test is done for all these 3 waveforms directly to the connector, the metallic connector of the equipment. For this sort of testing, is done with the EUT powered on. The cable bundle test is done for all the waveforms, and this is done by using various coupling mechanisms or clamps to induce these waveforms, all the 7 waveforms we mentioned earlier, onto the cable bundles. Okay. Here is the summary of the test methods, which I mentioned earlier. Let's look through these. I mentioned there are three applications of the cable bundle testing: single stroke, multiple burst. So single stroke is that when a test is being performed, you're just applying the waveform once. You're just giving a single stroke. In the multi-stroke, you're applying multiple strikes of the transient, depending upon the application. Typically, it's 14. So the amplitude of the first transient will be the highest one, and with each subsequent transient, the waveform amplitude will be going down. In the multiple burst, we apply 3 different set of the bursts, and each burst will consist of 20 transients. But if we compare with the multi-stroke versus multi-burst, in the multi-burst, the level of all the transients will be the same, whereas with the multi-stroke, as I mentioned earlier, with each subsequent transient, the level will decay down. Now let's talk about the test procedure. Depending upon how much time we have, I will talk about 1 or 2 test methods to describe how the testing is performed. Okay. Let's talk about the cable bundle, the interconnects. In a general test setup, you will be following the test setup description in DO 160. Typically, the lowest point of the cable bundle, which is 50 millimeter above the ground plane, it has to be raised from the ground plane by at least 5 centimeter. The recommended length to be included is at least 3.3 meter. The maximum length which can be used in a test setup is 15 meter. And for the cable bundle test, it's highly recommended that we keep the power leads no longer than 1 meter. If I could continue on, one more point I would like to make about the power leads is that in many cases, the power leads could be part of a cable bundle. And if the description by the manufacturer of the equipment is such that the cable bundle is always the part of the cable bundle assembly, then we will not, during the testing, try to remove the power cable from the cable bundle and test it separately. Only thing we would do is to the point during the setup where the power cable has to be connected to a listen, we will remove it from the cable bundle, have it go through the listen, and when we apply the transients, we'll apply the transients as a whole onto the cable bundle. However, if there is no description or manufacturer declares that the power cable has to be tested separately, then we'll detach it from the cable bundle and do a separate test on the power line and do a separate test on the bundle itself. Okay. Continuing on, let's talk about test procedure for pin injection test and the cable bundle test. As I mentioned earlier, pin injection tests are for waveform 3, 4, 5A, and the cable bundle will be done for all the waveform from 1 to 6. This is an example of how the verification is done of the generator for the cable bundle. So the point here is that even though a test generator, and I have a couple of slides at the end where I will describe briefly what are the options for test generator which are commercially available in the industry. Even though the test generator can be sent out for a calibration to a third party, however, the standard dictates that before each test, before the testing is done, the waveform is verified, because considering a cable could get damaged, considering a probe may take a hit if somebody accidentally dropped the probe on the floor, so thereby the parameters of the waveform could deteriorate. So thereby it's extremely important to perform the calibration or verification of the waveform before actual testing is executed. So if you look at this, the block diagram, we could see that a transient is being applied using a coupling probe, and then using a voltage probe or monitoring probe, it's being connected to an oscilloscope for voltage measurement, and also a loop is being generated to monitor the current. And thereby we can monitor both the amplitude and the current waveform using this particular setup for cable bundle. In the actual testing, we're going to open up the loop, and using the clamp, the induction clamp, we're going to apply the transient directly onto the cable at a specified distance. And then we're going to continue monitor the waveform using voltage probe and a current probe at a certain distance from which is 5 to 15 centimeter from the EUT port. The intent there is to make sure when the transient is being applied, it meets the amplitude and it meets the waveform requirement. And while the testing is being performed, obviously, we monitor the device, we monitor the avionics equipment for any signs of degradation of performance. And if there's any degradation of performance, during the testing, we report that. And our threshold has to be determined to ensure the transient doesn't happen. And like any immunity testing, any susceptibility testing, threshold will have to be documented as part of the test procedure. This is the verification setup for a ground injection waveform. Ground injection test waveform. So a loop is being generated using a transient generator. The waveform is being applied to the loop, and then using a probe and a monitoring current clamp with the help of an oscilloscope, the waveform parameters are verified and determined that if it meets the specification. And based on once the verification is done, using the setup very, very similar to my previous slide, the actual testing will be done. At this point, I'm going to conclude my presentation. Just very briefly, we'll go over a summary of my presentation. We talked about there are 7 waveforms, there are 5 test levels. Testing is done using 3 test methods: direct cable induction, ground injection, and there are 2 main categories of the testing, which is pin injection and cable bundle testing. And before that, we talked about what's the need to do the lightning testing and why it's becoming more and more important, keeping in mind that the trend we are seeing in the industry that large number of manufacturers are relying on the composite materials with the commercial aircraft design. I mentioned that I'll talk about the lighting system we use. At MATLAB, we have lighting system from 2 different manufacturers. One from the Thermo Scientific, which is an LTS system. It's a level 5 system. We can go all the way up to level 5. Then these are some of the clients. Recently, to increase our throughput, we bought another level 3 system from another vendor, which is the Solar Sciences. That generator allows us to do all the waveforms. The only downside is that there is only level 3. So we have one level 3 system and we have one level 5 system. At that point, I will conclude my presentation. I really appreciate your time and listening to me for this particular topic. Benabi, back to you.
Okay, thanks, Asad. That concludes the presentation portion of the webinar. Tomorrow, an archived copy of this webinar will be available on metlabs.com. We will send a follow-up email with a link to the file. Now, we will answer questions. If you have a question, please type it in the questions area of your control panel. For questions we can easily address now, we will read the question aloud, then give the answer.
Okay, I have one question, and my apologies if I misunderstood the question. It's been a little bit seems incomplete. The question is about the servo motor controllers. What I'm understanding is that I believe the question is if the lightning testing will be applicable to servo motor controllers. My understanding is yes, lightning testing is absolutely applicable to servo motor controllers. Again, my apologies. I wish there was more description and I could talk a little bit more about this. If I did not completely answer your question, please send us your question with the email to Bernardi, and we'll get back to you with more details.